In this video, our aim is to learn to use function notation and to understand why that is a good thing to use. Before we can do that, however, we need to have a discussion about domain and range, and also a quick discussion about some number theory things. So we're going to start with some number theory things. I'm going to sort of explain to you things you already know. And that is, the first numbers you learn are like, normal counting numbers you can count using your fingers, like 0, 1, 2, 3, so on and so forth. And they're actually called, so put some dots here so they keep going. This set of numbers is actually called the natural numbers and is represented with an N, the natural numbers. So let's represent that with a circle. They're our natural numbers. After that, you learn about the existence of negative numbers. So you add to that set some negative numbers, like so you'll include -1, -2, -3, and so on. But you'll also include the ones you had before, like 0, 1, 2, 3, and so on. That keeps going in both directions now. So both directions. So that's our new set of numbers, and these numbers we call integers, and we represent integers with a big Z. So maybe I'll write natural numbers here. Natural numbers. These ones are now integers. So the integers includes the natural numbers, and it adds the negatives. So there we go. There are our integers. Now, after you use integers, or you also know that now we have another set of numbers that includes the integers, and it's anything you can make with an integer divided by another integer. So, for example, you might have a half, because 1 and 2 are both integers. You might have 1/2, because 1 and the 2 are both, sorry, we already have that, 1 and 3. So a third. You might have a quarter. You might, keep going up. You might have then 2/3 and 2/4, and you can keep going. So and you can also have these negative ones here. You can have -1/2. You can have -1/3, and so on and so forth. So all of these numbers here, this new set, we call those rational numbers. Rational. They're our rational numbers, and we represent those with a big Q. Big Q. So they incorporate integers and add fractions. Rational numbers. Then there are some more numbers that we have after that as well. They include things like the square root of 2. Whoa, the square root of 2. So these ones are irrational because they're not rational. Square root of 2 is one of them. Another one, like the square root of 3, you might have the cube root. Whoops, the cube root of 7 would be one. You've also got special numbers like pi and like Euler's number, E, and those sort of numbers. So these ones we call irrational. So these numbers are irrational if you count them but not the rational numbers. But if you include the rational numbers, and of course rational numbers includes integers, which also include natural numbers, so if you include them, including everything, we now call these the real numbers. They're the real numbers, and we give them a big R for real. Now, if the next set after this, real numbers we will use in this Year 11 methods course, but the next set after this we won't use. It includes the number I, where I equals the square root of -1. So it includes anything that's got I in there, because of course you can't have the square root of -1. So that's what we call imaginary if you only include it. But if you include everything else as well as imaginary, so if we're including, now we're including everything, including imaginary numbers, then we call this complex. So these are complex numbers. And to represent complex numbers, we use a big C. So there we go. Here are all of our different sort of sets of numbers, if you like. And we need to use these when we're talking about domain and range, which I shall do now. Okay, so the domain and range. Well, the domain is just any possible x values, and the range is any possible y values. So it's pretty easy. Let's have a look at an example. So here we go. Here we've got a quadratic, and the graph is just y equals x squared plus 2. So the domain is any value that you can put in for the x value. And you notice here you can put any number in. You can put 1, 2, 3, the natural numbers. You could put -1, and it would go in there too. So you can put in the integers. Or you could put in a half, or you can put in -27 over 6, and that would work as well. So you can put in the rational numbers, or you can even put in x to equals pi. That's somewhere around 1, 2, 3, somewhere around here, and that gives you a value as well. So you can actually put in any real number for this example. Any real number will work. So here for example 1, the domain, and we can just write domain equals the real numbers. You can put in any real number. Now, the range, however, is a little bit trickier. So you see how it goes from 2 is the smallest number, but then it can be anything higher than 2 all the way up to infinity, if you like. So it can go from 2 all the way to infinity. So there are a few different ways we can write this. So range, we can just write RAN. So the range, it starts at 2, so it can be larger than or equal to 2, and it's y that we're talking about because the range is the values of y, and go up to infinity. So that's one way of writing it. Another way of writing it would be saying that y is in, so this little e looking thing, it's actually the Greek letter epsilon. It is like y is part of the set that goes from 2 to infinity. So, and I'll use a square bracket here because that says it includes 2. So square bracket means includes. And I've used a round bracket for infinity. Round bracket generally means doesn't include. And just by convention, you use that when you've got infinities as well, because infinity is more like a concept than an actual number. So you use doesn't include for that one. So there we go. That's example 1. Let's have a look at a second example. Whoa. Okay. So second example. So here we go. I've written my equation down here, and it's the same equation, x squared plus 2. So x squared plus 2. But I've also said that x has to be between 1 and 3. And you can see that that occurs with the graph. So here at 1 is where it starts, and 3 is where it ends. So here, for example 2, the domain is between 1 and 3. And it square brackets because it includes 1 and 3. Now let's have a look at our range. So our range, we can no longer just sort of easily read it off. This time we're actually going to calculate what the range is. So you can see that the smallest value occurs when x is 1, and the largest value occurs when x is 3. So for this particular example, we've got x squared plus 2 as our equation. If we put 1 in, then we've got 1 squared plus 2, and that equals 3. And if we put 3 in, 3 squared plus 2, plus 2 equals, that's obviously going to be 9 plus 2 equals 11. So our range is between 2 and 11, and it includes 2 and 11. So let me just do another very quick example here. Example 3. Let's suppose we have the equation y equals 2x plus 1, 4x is larger than minus 2. Oops, let me start this again. Minus 2, x is larger than minus 2. And it's smaller than or equal to 3. So 2x plus 1, it looks a bit like this, where it cuts through here at 1 and through the x-intercept at minus a half. Okay, so here we've said that x is larger than minus 2. So here at minus 2 is where it starts, but it does not include minus 2. So when it doesn't include minus 2, we put an open circle there at minus 2, so that we know that it does not include that point. But here it goes all the way until 3. Oops. And it does include 3, so you put a little closed circle there to make it really clear. Closed dot, to make it clear that it does include 3. So for this one, our domain is equal to, now we need a circular bracket because it does not include minus 2. And then here it does include 3. So you can do a 3 with a closed bracket. So it's okay to just write domain equals this. A more sort of sophisticated way is to say that the domain is when x is in the set of minus 2, 3. Within that set is also another way that you can write it. Then you can do the range in a similar way. You've got to find out what is x going to be when, what's y going to be when x is minus 2. So if x is minus 2, then y is minus 4 plus 1 equals minus 3. So what? And you can see from the graph that's going to be the smallest value. And it doesn't include it, so the smallest is minus 3. And then when x is 3, we're going to have y is equal to 6 plus 1 equals 7. 7, and it does include 7. So there we go, we use those closed brackets for that. Okay, now let's have a look at function notation. So here it is, and let's go through it bit by bit. So first, it gives us the name of the function. So this is kind of like the name of the function. So it kind of reads the function f, and then these two dots kind of represents such that. So here the name of the function is f. So you say the function f is such that, and now the next bit here we have is, this bit here is the domain. So it's the function f is such that for the values between 0 and 7, not including 7, they, and then the arrow is kind of like map to, they map to. So they map to these values will become some other values because of the function. So it's kind of like the idea of the function machine. Here's our function f, and some values will go in, and they'll give out some other values. So it's sort of saying these values will go in, 0 to, our domain will go in, and they'll give out some other values. And so it's saying they will map to something else. And here this R, so I'm running out of arrows, but let's just do one. This R here, this R is what's called the codomain. Codomain. So it's important to realize this R is not the range. Okay, it's not the range after the arrow. It's just, it's a set of numbers that the range is in. So the codomain is like the range is in here. The range is in here. In other words, the codomain contains the range. The range is in here. Okay, so obviously lots of things are in the set of real numbers. So the most common codomain is probably going to be the real numbers view. So it's like saying 0 to 7 are going to go into our function machine. Our function machine is going to spit them out somewhere in the real numbers. So this is going to go they're going to be in the real numbers somewhere, but they're going to be their own set. Or another way to sort of show this graphically is, suppose this is the real numbers here. Our answers might only be this little section of the real numbers over here. Might be your range, might be just this bit here of the real numbers. So that's the codomain. And then here we've got this whole bit is sort of like the rule for the function. So that's the rule for the function. It's the bit that we've been using again and again. So let's just say that's the rule here. This whole bit is the rule. Oops. That whole bit's the rule, where x is our variable, I guess. Variable or dependent variable, if you like. So variable, and so this part here is really our rule, and that's the bit you've seen lots of times before. So, so let's actually sketch this thing using our graphics calculator. So, our CAS calculator. So, just one moment. Okay, so here's our function, and we're going to sketch it on our graphics calculator. So I've opened up a new graphs page. First thing I'm going to do is put in the rule. So same as usual, put in the rule. We've got x multiplied by x minus 5 all to the power of 2, or x minus 5 squared, I guess. Now what I need to do is tell it, though, the domain. So domain is between 0 and 7. So I've got to, see these blue things here? We've got to go into those, so control there. Now I've got these things to choose from. This line here, the downwards line, it means given. So we're saying the function is this, given that x is going to be between 0 and 7. So we've got 0 back into there. So now we need to choose, is x greater than 0, or is it greater than and equal to 0? And here it's greater than or equal to 0 because it includes 0. Then x. Then for the 7 bit, we need to say it's smaller than 7, but not including 7. So here up, what we've typed in is the function of x equals x times x minus 5 squared, given that x is greater than or equal to 0 and smaller than 7. So there we go. So press enter, and this is what we have. Oh, we might need to zoom out a bit. Here we go. So there we can see the whole thing. And you can see that it starts here at 0 and it just finishes here suddenly there. Now, a couple of interesting things to note here. We've got a maximum value of whatever this is up here. That's our maximum value here. But there's also this little point which comes to a maximum. Now we call this point a local maximum because it's not the overall maximum, it's just the maximum for the points that are around it, the local points. Similar over here, we've got, we're not sure which one of these is a minimum and which one is just a local minimum. We'd need to test that out by doing some calculations. So we can do this, we can find the local minimum maximum. We've done this before, so let's just quickly do it. Analyze the graph. Let's find the local maximum first. There we go. And now let's find the local minimum. There we go, there's that. Now to find these points on the extremities of the graph, we can do that too. We just go into Menu, Trace, then we want to go into Graph Trace, and then we can just put the number in, press the number that we want to graph trace. So we put in 0. So it says down here x equals 0, so find out what y is when x equals 0. And there we go, it tells us that that is 0, 0. So let's do the other one over here when x is 7. So trace, graph trace. Now when x is, let's just try 7. Yep, there it is, x equals 7. And here it says undefined. That's because x cannot be 7. So, if we want to know what that point is, we can just put 7 into our equation and find it. That's probably the quickest and easiest way. So, if we've got 7, then it's 7 minus 5, that's 2. So we've got 7 times 2 squared, which is going to be 28. So we know that point is 28, even though using this, we can't find it unless we changed our equation so that it incorporated that point in our domain. So there we go. I hope that's been helpful, and I'll see you in class.